Dalton's law of partial pressures is actually really straightforward. Dalton's law of partial pressure says gases don't interfere with each other, so adding a gas doesn't change the pressure of the previous gas, it just adds pressure to the vessel. This is true as long as the gases don't react. If they do react, then the atoms or molecules combine, and so it changes the number of particles in the gas. But assuming that they don't react, then the total pressure is given by the individual pressures. The individual pressure of one gas is called a partial pressure, and we can actually find what percent of a gas is in there using pressures. And so what we have here is the mole ratio. Remember, we want to count moles of things, and so the mole ratio is the moles of gas A compared to the total moles of gas in the container. That's the mole ratio. And so if we take the mole ratio of a gas times the total pressure, that tells us the partial pressure of the gas. Similarly, the partial pressure of gas A divided by the total pressure of the vessel will also allow us to find the mole fraction of the gas in the container. So we'll work a couple example problems here. A 10-liter vessel contains 2.5 times 10 to the negative third moles of hydrogen, 1 times 10 to the negative third moles of helium, and 3 times 10 to the negative fourth moles of neon at 35 degrees Celsius. What are the partial pressures of the gases? You'll notice it's telling us an amount, it's telling us a volume, and it's telling us a temperature, and it's asking us for pressure. So PV equals nRT. Or pressure is nRT over V. Now, again, we want to make sure we're choosing a proper unit for R. It tells us a volume in liters, but then it doesn't ask us anything about pressure. So we can choose either. We could choose the R equals 8.314 kilopascal liters per mole Kelvin, or we can choose 0.0821 liter atmospheres per mole Kelvin. But the next question is going to ask us about atmospheres, so we might as well go with atmospheres. So nRT, so we have N is moles, so for hydrogen we have 2.5 times 10 to the negative third times, and we're going to use 0.0821, and then divide our times temperature. It says 35 Celsius, so that's 308 Kelvin, divided by volume, and the volume is 10 liters because all of these gases contain the 10 are contained in a 10-liter vessel, and this gets us a partial pressure, or the pressure of hydrogen. So I'm going to write that this way: pressure of hydrogen is equal to 0.00632 atmospheres. And you can do that for all of them, right? We just got to change the molar mass there. So the pressure of helium is going to be 1 times 10 to the negative third times all of that, and that'll get us 0.0025 atmospheres. And then the pressure, the partial pressure of neon is going to be 0.00076 atmospheres. And so then in part B, where it says what's the total pressure of all these things in atmospheres, all you have to do is sum up those three things, and when you do that, you get 0.00955 atmospheres. So partial pressures, pretty straightforward concept. Then we're going to use mole fractions, which again, not complicated. A gas mixture used for anesthesia contains 2.83 moles of oxygen, O2, and 8.41 moles of nitrous oxide, N2O. The total pressure of the mixture is 192 kilopascals. What are the mole fractions of O2 and N2O? Well, mole fraction, what part of it compared to the total? So O2 is 2.83 divided by the total of 2.83 plus 8.41. And that is equal to, let's see, 8.41 plus 2.83 is 11.24, and 2.83 divided by 11.24, 0.251. And then N2O, same thing, except now we have the 8.41 over the 11.24, and that is equal to 0.748. And then for B, what are the partial pressures of O2 and N2O? We can take our 0.251 times the total pressure, 192, and we get a partial pressure of 48.34, and we can take our 0.749 times 192, and we can get our partial pressure of 143.66. We can check, do those add up to our 192 that they start with? They absolutely do. So there's our partial pressures worked out. Easy peasy. Propane is used in gas grills to provide the heat for cooking. What volume of O2 measured at 25 degrees Celsius and 760 torr is required to react with 2.7 liters of propane measured under the same conditions of temperature and pressure? Assume that propane undergoes complete combustion. So this you could make really complicated, and you could say, okay, well, we can figure out based on the volume of the or the molar mass of propane, what its volume will be, and we can know. We're not going to do that. Avogadro's law, remember, tells us that under the same pressure and temperature, equal volumes contain equal particles. All we really need to solve this is a balanced chemical equation. C3H8 plus O2 produces H2O plus CO2. Right? That is the standard combustion of a fuel equation. We just have to balance it. I've got 8 hydrogens, so I've got to multiply by 4 to get 8 hydrogens. I've got 3 carbons, multiply by 3 to get 3 carbons. The only thing left to balance is oxygen. 4 plus 6 is 10, so we're going to go ahead and put 5. Now, this tells me 1 molecule of C3H8 reacts with 5 molecules of oxygen, but it also tells me 1 liter of C3H8 combines with 5 liters of oxygen. That's Avogadro's hypothesis. And so if I have 2.7 liters of propane, then I just need to multiply everything by 2.7, and 5 times 2.7, 35, carry that, 13.5 liters. So don't think we have to use all of the long complicated laws. If we've got a nice straightforward principle like Avogadro's law, we can make that